Modern cosmology rests on a massive contradiction. We are told that 27% of the universe is made of a mysterious, invisible particle, yet decades of searching have failed to produce a single detection. Look closely at the data from the world's most sensitive underground detectors. Facilities using massive vats of liquid xenon have run for years, waiting for a single weakly interacting massive particle, or WIMP, to scatter against an atom. The collision count remains at 0. In orbit, high-performance spectrometers scanning the galactic halo for particle annihilation signatures, the expected byproduct of dark matter collisions, have returned equally blank results. Detectors monitoring the solar core for high-energy neutrinos, the predicted exhaust of trapped dark matter particles, find only the standard emissions expected from nuclear fusion. And when protons are smashed together at near light speed in the Large Hadron Collider, the energy ledgers balance perfectly. The missing energy signatures required by supersymmetric dark matter models have never materialized. These are the most precise scientific instruments in human history. Their continued failure to find a particle suggests that the baseline hypothesis of standard cosmology is functionally broken. Particle physics has now reached the neutrino floor. At this level of sensitivity, regular background neutrinos mask any potential signal, making further direct detection attempts essentially futile. This dead end requires a shift in how we understand the vacuum. Dr. Rajkumar Dalgoda's dialectical deterministic coherent supermicroton field theory, or DDCSFT, proposes a rigorous mathematical alternative to the search for discrete matter. DDCSFT posits that dark matter is an emergent structural distortion of the vacuum itself, rather than an external entity drifting through space. This reorients our perspective from hunting a discrete, elusive particle to observing a localized state change in the fabric of spacetime. Space is structured as a spacetime vertex voxel lattice composed of the supermicroton field. This lattice's synchronization is measured by the Dalgoda Coherence Index, DCI. As gravity increases, thermodynamic noise stabilizes. At absolute saturation, DCI equals 1, vertices lock into a rigid, continuous fluid structure. Because this newly fused structure resonates at frequencies far beyond the electromagnetic spectrum, it possesses zero electromagnetic coupling, rendering it incapable of interacting with or reflecting light. What we perceive as dark matter is the localized fluid state compression of this ubiquitous quantum lattice. This lattice compression requires an extreme, concentrated source of gravitational stress to force the voxel vertices into absolute coherence. The supermassive black holes at galactic centers act as the primary engines for this process, generating a massive torsion vortex through their extreme rotation. This frame-dragging effect propagates outward from the singularity, dragging the surrounding spacetime and establishing a steep density gradient across the voxel grid. Compressing this lattice gradient generates a distinct binding energy, defined in the DDCSFT model as the fifth force. This localized fifth force provides the specific cosmic tension required to hold high-velocity stars in the outer galactic disk, solving the rotation curve problem without adding invisible mass. Under the extreme pressure of this central gradient, ambient vacuum energy undergoes a direct mass-energy conversion into the highly coherent fluid of the voxel lattice. The dark matter halo is the extended spatial footprint of a supermassive black hole's central vortex. If the dark matter gradient requires a central spinning mass, galaxies without active cores should possess zero dark matter influence. Ultra-diffuse galaxies like NGC 1052 DF2 provide empirical proof for this model. They lack both central spin and dark matter, with stars moving at standard Newtonian velocities. Observations of the bullet cluster show gravitational mass pulling ahead of the colliding gas. This displacement represents the elastic wave dynamics of the voxel fluid itself, propagating through the impact zone like a ripple through a medium. James Webb Space Telescope data supports this, showing early universe galaxies lacking dark matter because their central black holes hadn't yet achieved lattice-compressing rotation speeds. These anomalies confirm that dark matter is an entirely conditional phenomenon, dependent on local gravitational stress, disproving the existence of a ubiquitous background particle. Validating the non-local fluid dynamics of the voxel lattice required the AI physics discovery engine and the 105-qubit Google Willow chip. Researchers used 50 deep simulation correlations to test standard baryonic physics against the DD-CSFT framework. The high-coherent surface code of the Willow chip allowed researchers to flawlessly mirror the topologically protected state of the cosmos when the coherence index reaches 1. These trials identify quantum simulation as the only computational environment capable of mapping the nonlinear fluid geometry required by the DD-CSFT model. Acknowledging dark matter as a spatial gradient transitions the phenomenon from an astronomical mystery into a manipulatable engineering medium. By artificially compressing the voxel grid, we can create synthetic gradients to generate propellantless forward momentum. Theoretical models suggest that by artificially driving the DCI towards saturation in a controlled environment, we can tap the background energy of the voxel grid, effectively extracting power from the local geometry of the vacuum. This DCI saturation also creates a state of topological protection. A localized field in this state would possess the structural rigidity of the galactic voxel fluid, deflecting kinetic and electromagnetic vectors that lack the energy to disrupt the lattice coherence. The multi-billion-dollar hunt for a dark matter particle was a necessary failure. It provided data required to reveal the deeper architecture of the void. The shift from particle detection to geometric analysis marks a transition in our fundamental approach to the vacuum. Physics is moving away from the hunt for discrete matter and toward the direct manipulation of spacetime itself.